quiz and a contest. So I'm not sure that everybody got the link. I wanted to have the organization send a broadcast on Pathable so that you all have the link. You got it? But just in case, on the session on Pathable, the last link is the link to the quiz. So hopefully someone in the audience here will go back home with a nice drone. Also, I made sure that flight regulations are such that LiPo batteries are sometimes complex to carry. So there is a special LiPo bag, safe bag, so that airlines will accept the battery. So you will be able to leave with the drone flying back home. Maybe with an extra, it's that big. So. Anyways, so I'm glad you made for this session, and I would like to cover a number of things, maybe a little bit broader than just OpenDataPlane, and maybe you think of OpenDataPlane as a network limited, but why not using it for storage? So you see, we will be covering a number of topics for ODP. There are a number of concepts around that are software-defined networking, software-defined infrastructure, and I've even seen software-defined memory. So you can have a few gigabytes of memory and consider you get it as a software-defined manner. There are many ideas behind those software-defined things, but one common aspect of all those software-defined something is that there is some level of abstraction of what this something is. And then as you use that abstracted something, there is some kind of backend that translates that to the appropriate technology. For networking, it has been a little bit more specialized in the sense that software-defined networking has been associated with OpenFlow. It's not really fair to say that, but ultimately when we talk about SDN, people almost all the time think of OpenFlow. And so OpenFlow is about loading a number of rules in a switch so that the switch handles the traffic based on those rules. Now it happens that the switch can be a software switch. So for example, OVS is a software switch that is also an OpenFlow compatible switch. So for hardware switches, when we deal with the rules that are pushed with OpenFlow to the hardware, the packets are not really touching the software. That's where the software-defined behavior comes from. When the switch is a software switch, there are two things happening. One is how the software defines the behavior of the switch, so that's the software-defined thing. And there is the actual switching done in software, and in that case, this is a software data plane. So OVS, if it's accelerated with DPDK, for example, becomes a software data plane that is doing things, but the software-defined architecture, the software-defined networking is about controlling that behavior from software outside. So the software-defined is about controlling the behavior, not really implementing something. So I may have lost you by being very general, so I will be focusing on the data plane itself, and I will be using this example, which is going from one port. Can I use my yes? So here on the left, we have the receiving optic. Then it goes to a hardware classifier. Then it goes to a hardware scheduler through some kind of hardware queues. Then it goes to a packet application, and then back to the hardware. So let's say that this is a logical journey of a packet from port to port. It goes through those different elements. With a software-defined dataplane, a software-defined dataplane application would actually configure all the hardware blocks in such a way that packets can flow from input port to output port without having any software involved. We can have even, in some cases, have very smart features applied, like IPsec and layer 3 forwarding. So in that case, let's assume this is a box at home or an enterprise box. On one side, the packet is received by the optics, goes to IPsec, being decrypted here, go to the layer 3 forwarding block, and goes inside on the intranet of the enterprise. So here the software has been used to configure the hardware blocks, to configure the behavior of the hardware blocks. So ODP API covers from the top left to the far right of all the hardware blocks. It covers the configuration and the behavior of all the components. That's what ODP controls. If there are hardware that does not have, let's say, IPsec hardware or layer 3 forwarding hardware, then the ODP API is such that those functions can be done in software, but that would be transparent to the application. Now, if we look at the traditional model for DPDK, that's a very different ballgame, because the hardware blocks like classifiers, scheduler, traffic managers, those blocks are on the cards. And you can't control exactly how the classifier works. You have some control of it through RSS, for example, but it's very limited. And the DPDK API then really is starting when the packet gets out of the network card and stops at the network card frontier, even on the outside area. You have some level of control of the hardware blocks within the card, but you have no vision, no visibility, no inventory of what are the available functional blocks, hardware blocks on the card. And this means that whenever you have an application, I mentioned this IPsec thing and layer 3 forwarding, essentially you get the packets out of the card and then you do something, the software is always involved in the packets. So with ODP, you can use ODP to create a 48, 50 gigabit switch and have a way to build software to control the packet flow within that switch. But with DPDK, you cannot, because the CPU cores are too much involved in the movement of packets. And one of the reasons is that it's not that because DPDK is this or that. The problem is the memory speed, the memory latency. If you look at the memory bandwidth has significantly increased for the past years. But the memory latency to get one cache line to 64 bytes is always almost the same. That's 50 nanoseconds, I would say, to take an average measure. And 50 nanoseconds, it's way too slow as opposed to if you're like at 50 gigabit or 100 gigabit, where each packet arrives at 6 nanosecond. Each packet is received every 6 nanoseconds, so the memory cannot cope with that. And so being a software data plane and not a software defined data plane, the model for using acceleration in DPDK is typically star-shaped. So you receive the packet in the application, and then you send this packet back and forth accelerators to get things done. While on the ODP side, it's really a streamlined version where all those acceleration can be orchestrated by the software, and the software not being involved in packet movement. So those are, I'm also an engineer, so you can nitpick what I'm saying and say, okay, I can write a special PMD and do things on my hardware. Yes, but then this is not the standard DPDK. You have to spend energy on controlling those specific hardware capabilities. Are there any questions on this so far? Yes? Let's try.
So going back to your previous one with the two NIC cards, it's my understanding that DPDK is a whole load system as well. So it's spinning the cores all the time, even if you're not even collecting packets.
Correct.
Whereas ODP can go to sleep, basically. It can go away. Is that true, or have I misunderstood?
It is true. Both methods are available. ODP does not mandate you do constant polling. You can do it if you want, but you can leverage schedulers. And schedulers are richer than just interrupts. In the context of SOCs, if you look at those, typically in the PCI world, the card will say, raise an interrupt, and then the software will get what are the packets available, or if you constantly poll, what are the packets available. With hardware schedulers, you can, and with a hardware classifier that is there, what you can get is a notification that a packet that you wanted arrived. So in that case, for example, you could have packets flowing through the hardware entirely, and for some flows you will get a notification of this type of packet you wanted arrived. Did I answer your question? Yes?
If hardware doesn't support hardware forwarding capabilities from port to port, in such case, ODP APIs is like similar like DPDK.
Absolutely. And there comes the confusion between the two concepts, because when there is no acceleration, DPDK and ODP are really, really close. But not that close, because then you have something else, which is, let's say, packet ordering. So if you have crypted traffic, you want to handle packet one after the other. So ODP comes with a number of packet ordering options. You can choose at least from 3 different packet options. By the way, I've developed many applications on DPDK. I haven't yet developed an application on ODP. So I know DPDK better than ODP. Sorry? But yeah. I have a DNS server that is running at 190 million requests per second on DPDK, and I want to see how it behaves on ODP. I'll come back to your question because I have another element to mention. So packet ordering is one, but also you have packet dispatching or load balancing. So if you have a tunnel, let's say a GTP tunnel, all the traffic, a GTP tunnel is on UDP encapsulation. So all traffic on DPDK will arrive on one single core because it's always the same UDP tunnel. So because of that happening, you have to design your application such that one core will be getting the packets, and then you will have to create some kind of queues and additional cores to load balance the work between a number of cores. This again is entirely available in ODP, not as something that you have to code, but you just use it. And if you have hardware support for that, you don't have one core which is pulling and then dispatching the work. The hardware just dispatches the work for you from the ODP API. So even though, let's say, when there is no hardware acceleration, DPDK and ODP are very close, but ODP comes with a number of additional things that you will need in real traffic load in telecom world. I'll come back to that, but you can move packet fast, but telecom operators are not just happy with having things go fast. They want to have things happen in a controlled way. And changing packet order for them is like crossing the streams in Ghostbuster. It's bad. So don't do that. So ODP is really helpful in providing you the technology from the beginning to do that.
So on the same diagram, do you have a complementary diagram that shows where ODP sits in relation to the same flow?
This one?
So ODP would control the classifier underneath and the schedule underneath?
Yes. At a point that, for example, you could say to the classifier, well, here is, if you find any ESP, well, IPsec traffic, send it to this IPsec block. If not, send it to the layer 3 forwarding block. So that's a classifier rule that you push to the hardware. And if the hardware does not support that, then the software will do it for you. And then this means that maybe there will be an ODP thread acting as a classifier and implementing the rule you asked. But then it's transparent for you if the classifier is there or if it's not.
So, but in the link diagram, it's really a background that wraps around the application.
Yes. Now, of course, if you know the exact card, if it's a smart NIC, you may design your own PMD and implement, tweak the things, leverage the hardware capabilities, but then that's not portable. And even to build it, it requires a deep hardware knowledge to do that. Not mentioning the fact that typically IPsec and crypto operation are asynchronous. So in addition to implement the crypto operations, you have to have an asynchronous event framework to handle, okay, here is the crypto operation that has finished. Here is so with DPDK, you don't have a common event framework, asynchronous event framework. You have to build your own. And I'm not saying DPDK is bad. I'm saying that it's solving a different problem. It's doing something very nice. As I said, for my DNS server, it's perfect. But for a telecom workload, I wouldn't use DPDK, I would use ODP. So a complement to a question I had. So I'm an engineer. I'm also a little bit of a marketing person, but at the basis, I'm a technical guy. So last year, I built a demo on IPsec, not on ODP, but that's not the problem. I'm going to talk about benchmarks. So the benchmark was about 160 gigabit per second IPsec on a server. So if you look at the market, you have to buy a Juniper box, $1.2 million to do the job. Now, if you do in software, you can do that for 200K. And I expect, I hope there are no lawyers here, so if you use some hardware from ARM, you will probably do it for 40K because of those hardware accelerations. But my point is about the benchmarking. When you push packets through this 160 gigabit per second system, it provides the 160 gigabit IPsec thing. Great. But that's individual packets that are not related to each other. So then what you do is, well, I have an application, and let's say a web application, and you test your system, and all of a sudden it's not anymore doing 160 gigabit per second, but it's doing 50 gigabit per second. You haven't changed anything. Long story short, the reason of this lowering of performance was because of the TCP ACK packets that were delayed to go back to the server. So the cores were not busy because the TCP algorithm was not opening the window. And because it was not opening the window, bottom line, the traffic, the throughput was 50 gigabit per second. It was not a limitation of the infrastructure, it was a limitation of the protocol. But now if you address that and change some infrastructure parameters, you configure your IPsec solution, then you're back to 160 gigabit per second. So here, there is one important thing about benchmarks that you will see in the press or in different areas. There are essentially packet benchmarks. And packet benchmarks are, bottom line, a very bad indication of the application performance because of many reasons. And if you take into account virtualization, there are many things at the crossing of this virtualization boundary, like support for GRO, GSO, and those aspects. If they are not supported, performance degradation will be significant. So for benchmarks, they have to be really, if you have a telecom workload, don't trust any packet benchmark. You will fail at designing your system properly. Now, if we look also in telecom workloads, you have many levels of encapsulation. So you may have VXLAN, MPLS, GTP, and your application. But then all those cards that are supposed to be handling VXLAN and others, then they stop working because of these multiple levels of tunneling. So again, benchmarks here have to be considered for just a pure indication of the raw performance, but definitely not the performance of the architecture itself. And why I say that? Because when you look at the end picture for applications, that's where the big difference between ODP and DPDK will appear. If you look at how packets are moved, okay, line rate is line rate. but application performance, application behavior will be different. So we released the ODP Monarch release in August. It's been now supported by a number of hardware vendors. Linaro has traditionally delivered, let's say, one thing, which is a reference implementation of ODP, which was then used by silicon vendors to implement their version of ODP. Now we will be also releasing, in addition to the reference implementation, we will be releasing 2 high-performance ODP implementation, hardware agnostic on ARM and x86. So both solutions can be used to build products. They can be used also to create application in VMs. So if you have a server form factor with ARM on different vendors, you will be able to use that version to build your application. And if there are any accelerations, then you may be able to use them in a transparent manner in the future. That's the goal. In addition to deploying those 2 high-performance versions for, I insist, ARM and x86, in addition to providing those high-performance implementation, we will also provide, in coordination with Open FastPath open source project, a high-performance implementation of the combination of the 2, so that then it can be used, as was described in the previous session, it can be used to accelerate any application. We'll be working also on other artifacts to work on networking infrastructure and to provide what we call reference platform builds, which are a set of packages that are bundled together to create the basis of a product for a VCPE or for a telecom edge node or for some other possible reference platforms. The roadmap for that. So Next Connect in March will be providing most of the functionality. So the Tiger Moth is the name of the next version, and we've also identified the version after that. We called it Brimstone. So that's we keep on using butterfly names, and we're really aggressively working on making making an IPsec demonstration full of load for Next Connect in Budapest. And Tiger Moth full release should be available. Well, we target to have it in September next year. So as I said, OpenDataPlane can be rich, and NVMe over Fabrics, there are no reasons why we wouldn't create something here, as performance of flash systems is such that you may need millions of IOPS on the block side to be pushed on the network. So for example, 240 gigabit of block traffic represents more or less 6 million 4K IOPS per second. So 5 million IOPS is more than what the kernel can achieve today, well, with a reasonable amount of cores. So what happened on the network side will probably happen on the block side, being handled on the user land. So I'm not saying that this is a roadmap, this is something that will be integrated in OpenDataPlane anytime soon, but that's really a direction that is seriously considered. And then we have many other topics, and why not having a ODP on Windows, leveraging Packet Direct. That can be also demonstrating high portability on the OS side, not just working on Linux. So even if Linux is coming today or tomorrow, we may have to work on other operating systems. And two very important additions to research areas are how we will take into account coherent acceleration, so what ARM, Mellanox, and others has announced, that's C6, CCIX. This will be a significant change in acceleration in general. How ODP will leverage reconfigurable hardware like FPGAs, and how ODP will control P4, how it will leverage P4 to deliver services. So those are important research topics that we are currently investigating. And I think I'm done, and we can have additional questions. Yes, if you use the regular application, you don't have any. So if traffic is not engineered to pass the benchmark, let's say this is multicast traffic, you know, from RFC, I don't remember this one, you know, for.
I think they said they use like a spine for it. If you just set that up for just spewing,
Yeah. So you engineer your traffic so that it's matching, it's going to all queues.
So it does not show the benefit of ODP if you do it that way. You were just creating
Yeah.
an unfair.
Yes, but then this comes back to my other comment on benchmarks. The current benchmarks on the market are unfair because they engineer the traffic so that it kind of fool the reader. So, okay, we can be, let's say, engineers and say the real workload would be that, but then we would have to explain why the other benchmark is kind of misleading the reader.
An analogy Secret breaks. Freeway with 6 lanes on it, right? And you're measuring the amount of cars that pass per hour. You load that freeway up with all 6 lanes, all full of traffic, and you say, I can do, you know, 1 billion cars a day or something. But in real world, you've got some people in the fast lane, people in the short, slow lane. My understanding on DPDK is as soon as you decide the slow lane goes to call 1, that's all it can handle. And as soon as you decide the fast lane goes to call 2, that's all it can handle. It's completely unbalanced.
Correct.
Any call can handle any lane traffic, right? So, and I just made it up on the fly.
Well,
That was my analogy.
you have both options even on ODP. If you want to handle the traffic that way, the DPDK way, you can. And if you want to have the traffic to be handled in a smarter way, you can also. But with DPDK, you don't have choice except writing your own load balancer because you know the traffic. But then that's unfair because this is not a generic application. This becomes a. Is it really an application? Because if you design your application to be matching the traffic that you will receive, This is not... Other questions? So again, hopefully I haven't said DPDK is bad. I haven't said that. I have said DPDK is fast, is doing its job properly, but that may not be what you need to solve your real-world telecom workloads or even real-world cloud workloads. And ODP will help in solving those. ODP, and if you combine it with OFP, even better, you will accelerate applications transparently without having to change the application. Thank you very much.